Hello. Hello, can you hear me now? Moin, can you hear me? Shall I start now? ठीक है ठीक Hello everyone. I hope you are doing good, healthy and safe in pandemic situation. After taking a break for a couple of months, we are resuming our webinar series now. I would like to remind you all we will be discussing different industries design and manufacturing issues faced by industries. Until now, we have discussed 3D assembly modeling, create a 3D part and insert it into complex assembly design. Then we created the 2D drawings from that and create the bill of materials on that. Also, we have performed the simulation on the part. We have also covered computer aided manufacturing topic. There we have discussed 2.5 and 3 axis CNC programming, and our last webinar was on reverse engineering where we use Geomagic Design X with the 3D scanner. I hope all of you in past were joining and attending our sessions. If you miss them, please coordinate to our team and we will send you recorded link of the webinars. Our upcoming webinar topics include advanced part modeling, complex assembly design and analysis, detailed drawing including bill of materials, advanced surface modeling, mold designing strategies, discuss sheet metal bending unbending issues that can be resolved by deformed length calculation method in the SolidWorks, which is a major issue in the industry right now. We will have two sessions on simulation as well, one for linear simulations and second for nonlinear simulation. And in last, we will do a webinar on 3D inspections, performing CAD to physical part analysis for quality control and generating the reports from that. We are Quality Solutions. As I mention all the time that it will not be possible for us to cover all the topics in details. Therefore, you can visit our training centers to attend classes for above courses and get the certifications. I am Muhammad Usama Siddiqui, responsible for technical support in the company. We are Quality Solutions, and our main purpose is to adopt innovative technology throughout the world and introduce them into Pakistan. Alhamdulillah, we are professional in computer aided designing, computer aided manufacturing, computer aided engineering, and having expertise in 3D scanning, reverse engineering, 3D inspection, and 3D documentations as well. We are also fully equipped with both hardware and softwares as well. You can call us for the services and assistance in any 3D scanning, 3D inspections, reverse engineering, or 3D printing, or also for CAD CAM purpose. Let's come back to the topic we are going to discuss today. Pick up the right additive manufacturing or 3D printing process. Before we start, I excuse in advance for the answers of your questions, which will be missed during the webinar as it may be a bit longer session, but but you don't have to worry about that. You can send your queries to our mentioned address and we will answer you there. What you are seeing on the screen is our agenda. The agenda will cover the following steps including 3D printing technologies. We will discuss dimensional accuracy comparison between technologies, and then we will also further analyze over the setting up the best orientation for ideal support structure. Also additive manufacturing general procedures we will discuss, and what material section selection should be while doing the 3D printing in different technologies like FDM, SLA, SLS. Also, we will discuss the functionalities and visual appearance results from the 3D printing, and in the end, we will identify by the manufacturing application in the market. I hope you guys can listen me clearly. I heard a message from a buddy saying that there is a voice behind. Is it clear for now? Moin, please, if you can confirm me about the voice clarity, please. I hope it is better now. Can you hear me now? Can you hear me now? Is it clear for now? I'm sorry for the noise. I hope that it's now clear. Uh, Let me continue the session. 3D printing. 3D printing is a process solid objects from a digital file. The creation of a 3D printed object is achieved using additive process where successive layers of material are laid down in different shapes. Object can be of almost any shape or geometry and produced from a 3D model or other electronic data information. When a person creates a 3D image or a CAD data model of an item into the software program like SolidWorks and then send CAD information to the 3D printer where the printer forms the item by depositing the material in layer starting from the bottom onto the platform, and in some cases the light or lasers are used to harden the material. So the steps followed in this process is it's not it's not just like an additive manufacturing takes virtual blueprints from computer aided design, that is your CAD, and first slices them into digital cross section for the machine to successfully use as a guideline for printing. After the machine reads the design and lays down successive layers of liquid or powder or can be sheet material to build the model from a series of cross sections. These layers, which correspondence to the virtual cross sections from the CAD model, are joined together or automatically fused to create the final shape. However, the strength, finishing, and accuracy of the 3D printed part is depend upon some important aspects that we will be going to discuss today. And this is how we get the final model from CAD. Even though the printer produced resolution is sufficient for many applications, printing a slightly oversized version of the desired object in standard resolution and then removing the material with a higher resolution, that is subtractive process, can achieve a higher resolution with good quality. So what you're seeing on your screen showing both results, the rough printing process and the surface finish after subtracting the rough material from that. So right now, methods and technology of computer aided manufacturing are fused filament fabrication, that is FFF, also known as fuse deposition modeling, we call it FDM, builds objects from the bottom by layering plastic that's heated in a moving extrusion head. SLA, also known as stereolithography apparatus, is optical fabrication or photo solidification or resin printing. This form of 3D printing technology used for creating models, prototypes, patterns, and production parts in a layer by layer fashion using photochemical processes by which light causes. The difference in SLA and DLP is the part extrusion orientation only. In DLP, the part protrusion is in inverted direction. Let me explain you the most common 3D printing methods used by the industry, and we will discuss all of them and presenting their dimensional accuracies of 3D printed part produced by them. In order to help quantify the accuracy of 3D printed parts, the parameter of accuracy variables like dimensional accuracy of calibrated machine, warping or shrinkage factors, and support requirements have test. Let's start with the FDM. FDM, the fuse deposition modeling, is best suited for low cost prototyping where form and fit are more important than function. FDM produced parts one layer at a time by extruding a thermoplastic onto a build plate. For large parts, this can lead a big variations in temperature across the build platform. As different areas of the part cools and different rate internal stress cause the print to deform, leading to wrapping or shrinkage. The solution like printing rafts, headbeds, and radii at sharp edges and corners can help to reduce this. Different materials are more prone to warping than others. For example, ABS is known to be more susceptible or warping than PLA. As we look at this chart, for both desktop and industrial 3D printers, thermoplastics require a higher printer temperature, which is more risky. Better to adding a radius on the bottom edge of the part in contact with the build plate is recommended. However, shrinkage usually occur in 0.2 to 1% range depending on material. Regarding the support required, essential to achieve an accurate part greater than 45 degrees, and the dimensional tolerances between the 3D printer that are of two types in desktop versions and are made for the industrial tolerances. The desktop tolerances will be of 0.5%, that you can say like zero point 0.5 mm, and for the industrial that is 0.15%, that is zero point 0.2 mm for the industrial. So right now in FDM there are lot of materials in which you can print. You can print in PLA plastics, nylon, PEEK, ABS, ASA, and there are categories in ABS and nylons as well, like nylon 6, nylon 12, nylon 12 CF. So there are variety of materials available for the FDM technology. The SLA printers use a laser to UV cure specific areas of a resin tank to form a solid part, one cross section at a time. These cured areas, however, are not at full strength until post processing with UV. Because of this, and the angle and the orientations that SLA parts are typically printed at, sagging of unsupported spans can occur. As one layer is built up at a time, this effect becomes cumulative, leading to the dimensional discrepancies sometimes seen in tall SLA parts. Dimensional discrepancies can also occur because of the peeling process used by some SLA printers. The pulling force during the peeling force can cause the soft print to bend, which again can accumulate as each layer is built up. Resin that have higher flexural properties means less stiff are at a greater risk of warping and may not be suitable for higher accuracy applications. When we took a chart and look here again for both desktop and industrial printers, the dimensional tolerances are of 0.5 and 0.15%, but its lower limits are zero point 0.10 mm for the desktop printers, and for the industrial application is 0.01 mm. Shrinkage is likely for unsupported spans where support is essential to achieve an accurate parts. Again, like FDM 3D printer technology, the SLA technology is also fully equipped with the lot of materials, and there are more than 10 to 13 resins type in which you can print. By the way, there is a question appear for me that if I said that SLA and DLP are both common technology and only the difference between them is the orientation. So the question is, if they have the same chemical properties, same material properties they can print with. I would like to see your answers on chat and then I will answer you on that. Now come to the selective laser sintering process, that is SLS printing. The SLS produce part with a high accuracy and can print designs with complex geometry. A laser selectively sinters powder one layer at a time to form a solid part. To restrict the likelihood of part warping or shrinking during printing. SLS printers used heated bill chambers that heat up the powder to just below the sintering temperature. This does still, however, result in temperature gradients in large SLS parts, where the bottom of the parts has cooled while the recently printed top layers remain at an elevated temperature. To further mitigate the likelihood of warping occurring, parts are left in the powder to cool slowly, often for 50% of the total build time. And with the technology, shrinkage usually occur in the 2 to 3% range. However, most SLS printers provide by the manufacturer allow for this in the design. The dimensional tolerances of the SLS is for industrial printers genuinely, which gives you 30.3% of the lower limit, that is zero point 0.3 mm. Shrinkage usually occurs in the 2 to 3% of the range, and there will be no support required during the 3D printing, as the laser directly harden the part and the rest of the part remains same, so that the remain powder create a role as a supported material. So there is no need for the SLS 3D printing technology to use a support material. Right now, you can print the SLS with the nylon, like nylon PA12, PA1108, SLS TPU rubber using the SLS technology. Now come up with the metal printing, specifically DMLS and SLS. The DMLS is the direct metal laser sintering method. Use a use a laser to selectively sinter or melt powder to produce metal parts. Much like SLS, metal printing produce parts one layer at a time in a controlled and heated the environment on industrial sized machine. This layer by layer construction, coupled with the very high temperature involved in the process, and creates extreme thermal gradients. And the net effect is that stresses are built into the part. As a result, metal printed parts are at a high risk of distorting or warping, meaning good design practices and part orientation are critical to achieve an accurate part. Unlike SLS, support structures are vital to minimize distortion of the part during production. Hence, parts are also generally built upon a solid metal plate and need to be removed once the print process is complete. A sound understanding of the process is required along with solid and lattice support structures to keep the part securely attached with the printer bed and stop it from detaching. Most parts are also stress relieved, like via heat treatment process. You can remove them. And after they are built and before removal from the build platform, doing as follows: the crystalline structure to relax, preventing failure later. Since the cost of metal 3D printed parts is so high, simulations are often used during the CAD design to validate the accuracy of design before starting the printing job. The dimensional tolerance is zero point 0.1 mm in metal 3D printing case, and having the part at a high risk of shrinkage or bracing or warping, and support as well are used to help reduce the likelihood of this occurring. Further, the support is essential to achieve an accurate part. Material you can print for both SLM and DMLS 3D printing are stainless steel, titanium, bronze, cobalt chrome, aluminum, Inconel, Incolon in 625 and 718, merging steel. So all of these material you can print with DMLS and SLM technology. Right now we are describing over the 3D printing technology, and inshallah in our upcoming webinars we will be discuss the difference between the technologies like SLA and SLS, DMLS and SLM. But currently we would like to deliver you the information. Now, selection by correct 3D printing process. 3D printing is an umbrella term that encompasses multiple processes. Every 3D printing process has its benefits and limitations as well, and each is more suitable for certain applications than others. We have approached the process selection from three different angles: the required material should already known, the characteristics of the end part like physical or which virtual should be defined, and certain process capabilities like accuracy, build size, etc. are required. So let me start by selecting a process by material. 3D printing materials usually come in filament, powder, or resin form depending on the 3D printing process used. Polymers, plastics, and metals are the two main 3D printing materials, while other materials such as ceramics or composites are also available. Polymers can be broken down further into thermoplastics and thermosets. If the required material is already known, selecting a 3D printing process is relatively easy as only a few technologies produce parts from the same material. In those cases, the selection process usually becomes a cost versus properties comparison. Thermoplastics are best suited for the functional applications, including manufacturing of end use parts and functional prototypes. They have good mechanical properties and high impact and chemical resistance. They can also be filled with carbon, glass, or other additive to enhance their physical properties. 3D printed engineering thermoplastics such as nylon, PEI, and SAF are widely used to produce and use parts for industrial applications. SLS parts have better mechanical and physical properties and higher dimensional accuracies, but FDM is more economical and has shorter lead times. As a rule of thumb, the higher up a material is in the pyramid, the better its mechanical properties. Like peak and PEI have the better mechanical properties than PLA, PE, ABS, PS, and the harder is generally is to print with higher cost. The next process should be the thermosets resins. The resins are better suited for applications where aesthetic are important, as they can produce parts with some injections like surfaces and fine details. Generally, they have high stiffness but are more brittle than thermoplastics. So they are not suitable for functional applications, especially resins are available that are designed for engineering applications mimicking the properties of ABS and PPP or dental inserts and implants. Material jetting produce parts with superior dimensional accuracies and generally smoother surfaces, but a higher cost than SLA or DLP, and both processes use similar photocurable acrylic based resins. Processed by the metals. Metal 3D printed parts have excellent mechanical properties. How? It can operate at high temperature. The freeform capabilities of 3D printing make them ideal for lightweight applications for the aerospace and medical industries. The DMLS or SLM parts have superior mechanical properties and the tolerances as well. But binder jetting can be up to into 10 cheaper and can produce much larger parts. Other materials can be 3D printed, but they are not as widely used since their applications are limited. These materials include ceramics and sandstone in full color with binder jetting. Here is the tip: due to the additive nature of the technology, 3D printed parts will often have anisotropic mechanical properties, meaning that they will be weaker in the Z direction. I will show you in my next slides. For functional parts, this characteristic should be taken into account during design. So the process for the binder jetting printing starts with the power is deposit into a tank first, and then inkjet applies to the binder where each layer is printed fast and the powder is recoated after each repeat until the parts complete. And after that, and after that, once the part is completed, we put this into the clean tank that is also called the subtractive tank to remove the extra material on the part and achieving the good finishing surfaces. We can also select the 3D printing technology by a process of use of case. It is important to determine early in the selection process whether the main design consideration is function or visual. This will help greatly in choosing the most suitable process. As a rule of thumb, thermoplastic polymer parts are better suited for functional applications, while thermosets are best suited for visual appearances. So by use of case, we will first discuss about the functionality. When designing a part or prototype that will interfere with other components in the assembly, it is important to define the necessary level of tolerance. Otherwise, when there is no tolerances between the part you define, the parts could not be seated exactly during the assembly. As a rule of thumb, selecting a process with a higher dimensional accuracy will increase the cost as well. Another option is to finish feature with critical dimensions or small details after 3D printing, for example, by drilling holes or tapping threads. Overall part strength depend on different mechanical and physical properties. To simplify the selection, the material tensile strength can be used as a guidance when high strength and stiffness are required. Metal 3D printing or FDM printing reinforced with continuous carbon fibers are the best solution for that, but engineering 3D printing materials are available with special properties such as heat resistance, flame resistance, or chemical resistance, or that are certified as biocompatible or food safe as well. But the flexibility can be defined as either higher as either as either higher or elongation at the break. But where the thermoplastics such as TPU are available in SLS and FDM, or as low hardness, where materials with a rubber like feel are available for SLA, DLP, and material jetting. And in last, the use of case is very important with the depends on the visual appearance as well. So for both SLA and DLP and material jetting as well can produce parts with a smooth injection molding like surface. The main difference between the two processes, apart from the cost obviously, is that support in material jetting is soluble, while in SLA and DLP, it needs to be removed manually after printing, leaving small marks on the surface that need to be post processed, like sanded or polished later. But with the very small parts, with the thin, having the thin layers or thin walls, it become complex to remove the surfaces, extra surfaces that has been printed. I mean the support material. When you try to put them out, maybe your surfaces will be disturbed. Also, for the material jetting fully transparent parts, while SLA DLP parts are printed with semi transparent and can be posted to be almost 100% optically clear. Parts with especially texture such as wood-like or metal-like finish can be printed using wood fill and metal fill FDM filaments, like rubber-like part are also soft and having shore hardness less than 70 and can bend and compress as well. But luck the performance of true rubber is exists as well. However, the material jetting and binder jetting are the only 3D printing process that currently offer full color printing capabilities. Material jetting has the advantage as it offers material with better physical properties as well as multi material capabilities. Another option is to prime and paint the model after printing for use an FDM printer with dual extrusion capabilities for two colors only, not more than that. Now, we can also selecting a process by manufacturing capabilities of the 3D printing technology. When the model design is already finished, the capabilities of each 3D printing technology will often play the main role in the process selection. It is important to have an overview of the fundamental mechanics of each process to fully understand their key benefits and limitations. Here are some handy rules to help you interpret the data: the dimensional accuracy, checking the build size, and the support material information. Dimensional accuracy is connected to the level of detail to each process can achieve, and the build quality of each printer. The process that offer higher accuracy can usually create parts with finer features. Industrial grades machines have higher accuracy, as I informed you before, and repeatedly than desktop printer. So if we see the comparison between the FDM, between the desktop and industrial 3D printers, that the desktop printers is only available in FDM, SLA, or DLP technology. However, the industrial level technology included FDM, SLA, DLP, SLS, material jetting, binder jetting, DMLS, and also SLM. So as you can see on the screen, the dimensional accuracies of all of the technologies in desktop 3D printing as well as in industrial 3D printing is that right now the FDM technology give you the lower limit with zero point 0.5 mm, but with the industrial 3D printer it can give you zero point 0.2 mm. With the SLA, which is which can be said that give you prototypes that can be used for functionality purpose, not with the desktop versions, but yes, in the industrial versions you can use DLP or SLA for the functional parts because it gives you the dimensional accuracy of 0.05 mm. Please keep remember that these are the lower limits, not the average. Depending, because it is depend on your build volume of your part. The bigger your part, the bigger the lower limit. Then the dimensional accuracy for the SLS printing on industrial level printer is zero point 0.3 mm, whereas for the material jetting it is 0.05 mm, and again 0.3 mm for binder jetting only for sand printing purpose. And with the SLM or DMLS printing, it give you zero point 0.1 mm dimensional accuracy. The build size determines the maximum dimensions of the part that a printer can produce. For components that exceed the typical build size, consider migration to an alternative technology or splitting the part into multiple components that can be assembled later. But for that you must have lot of experience with the 3D printing, and then when you do the 3D printing of two parts in a splitted way and then you will merge it, you will understand its application better. The need of support structure or support materials determines the level of design freedom. So the process that require no support, like SLS, or dissolvable support like material jetting or dual extrusion FDM industrial or desktop 3D printers, have a fewer limitations and can produce free form structures with great ease. But for the SLA DLP and for material jetting and for the DMLS or SLM, the support material is always required, which can be removed manually because the support material in this technology are the same as the printed material and which can be removed manually. But in the material jetting technology, the supporting material is dissolvable, which is different, and also for the FDM. Another important aspect to consider when choosing a technology, the technology is the impact of layer height. Due to the additive nature of 3D printing, layer height determines the smoothness of 3D printed surface and the minimum feature size a printer can produce in Z direction using a small layer height also make the stair stepping effect less prominent and helps produce more accurate curved surface. So typical layer thickness with the FDM, you can go from 50 to 400 microns, and the most common operations for the FDM 3D printer commonly used for 200 microns because we have to consider the time of the part, because if we give the more accuracy and the less layer height, your printed time will be more. Seems like in SLA DLP, it give you layer thickness range from 25 to 100 microns, commonly use 50 for the time saving. With the SLS, the range is 80 to 120 micrometer, and the recommended is 100 micrometer. With the material jetting, give you 16 to 30 microns, and also with the binder jetting, it gives you 100 microns. With SLM or DMLS with 30 to 50 microns. So what we have figured out here, that the functional parts that come out from the 3D printer must have layer thickness minimally below 50 microns. Otherwise, the layers results will be rough, there will be no good finish, and the accuracy will also matter. Now here we have a question for you. What do you think, which layer height gives you the strongest 3D prints. I hope you can see the poll on your screen, and you have 60 seconds time to answer your questions. I will wait for you for 60 seconds. I hope you have done with your answers. I'm really sorry for that. I thought Mr. Muin will raise the poll. Now, I hope you can see this on your screen, and you have 1 minute to answer. Polls end, and you can see the results on your screen. Please keep remember your answers. Before answer that, let me tell you that here we will discuss an analytical report posted on World 3D Printing platform, but the study is specific for FDM technology only. Which layer height has more strength? Is it 0.05 mm with the good surface finish, or zero point 0.4 mm? Have you ever asked yourself what the influence of the layer height you set in your slicer. The slicer has not the slicer has on the strength of your 3D prints a studied printed samples with layers ranging from all 5 millimeters to point 0.4 millimeters and measure their strength on a universal test machine to check which one is the strongest. The most of the people set the layer height to adjust the amount of detail of their 3D prints and how smooth the surface finish shall be in the end. Thinner layers give you less of a stair step effects but will increase the print time. Actually, the printing time is inversely proportional to the layer height. So, using layers half the thickness will be more or less double the print time. Most of the people set the layer heights to adjust the amount of details of their 3D printers and how smooth the surface finish shall be in the end. Thinner layer give you less of stair steps as you can see on the screen, but will increase the printed time. So the printing time is inversely proportional to the layer height. So using the half the thickness will be more or less double the print time. If we are taking about the use of the strength at this point, I actually mean layer adhesion. So how could the individual layers of material bond together? Thinner layers could be stronger because the material is squeezed out more from the nozzle. And due to the low distance between those and the previous layers, once the materials and helps with bonding. Since you extrude less plastic in a given amount of time, the material stays in the melts for longer and therefore properly and evenly warms up and melts also. The density of part within the layer could be higher due to smaller gaps between the lines of already printed materials. Though, especially the point that the material stays melted for a longer period of time and therefore potentially degenerates in an argument that thicker layer might give you spots with higher strength. With thicker layer, the position tolerance of z axis doesn't play such a big role because the tolerance is a smaller percentage of the total layer thickness. What I mean is that, for example, a 5 millimeter micrometer thickness is way worse and could result in plus minus 10% over or under extrusion, whereas the 5 micrometer tolerance, its 250 micrometer layer thickness, give you only plus minus 2%. Then there's the statistical aspect. With thicker layer, you consequently print less layer for the same part. This decreases the risk and that in one layer something went wrong, which is the end will be the location with a failure start. This concept is called a statistical side effect actually. In research, all parts were printed on PLA using a hardened steel nozzle and their default settings. In the test, we choose the standard 0.15 millimeter and set three parameters and then only varied the layer thickness and increase top up and bottom layer to get a consistent wall thickness. We ended up the testing six different layers height starting from 0.05 mm, zero point 0.1 mm, 0.15 mm, zero point 0.2 millimeters, zero point 0.3 millimeters, and zero point 0.4 mm. And we have never been printed with layer then zero point 0.4 millimeters is beyond what you should print with the nozzle that has the same diameter. As mentioned in the beginning, printing time is inversely proportional to the layer thickness, but the first interesting results was that not all the hooks weighed the same. As you can see on the screen, that the higher the layer thickness, the less part weight, which is probably explainable with the fact that thicker layer feature has more gaps and are therefore less dense. We will keep these values in mind when we take a look at the strength later. Another results that was interesting for us is the print quality, which is in my opinion didn't improve. As you can see on the screen, the thinner the layers got, however, the side surfaces usually look better since the last watch out, but all in all, the sweet spot in our opinion was 0.5 mm. Another thing that we noticed that the color of the part started to get irregular, especially at 0.5 mm. This is probably because the material is in molten state for the longest amount of time, messing with the pigment and maybe even the base polymer. Please give me a minute. It's actually the azan near my place. Uh, Please continue. So now all the samples that we have tested one by one into DIY universal test machine and loaded them very importantly all at the same speed until they failed and meanwhile record the load values. At first we put the part on XY flat orientation and print all above mentioned range. Look at the results from zero point zero 0.05 millimeters up to zero point 0.4 millimeters. So with the test, we got the results that with zero point zero 0.05 millimeters, our hook breaks with the XY flat orientation at 79 kilograms of load, whereas at zero point 0.1 millimeter layer thickness, it breaks at 85 kilograms, and in 1 point and in zero point 0.15 millimeters it breaks on 80 kilograms. Whereas you can see after zero point 0.1 mm the load values go downside. So at zero point 0.2 mm the load reduce to 78 to break the hook, and at zero point 0.3 it reduces at 6 kg, 66 kilograms, sorry. So what is the ideal right now? From zero point zero 0.05 millimeters up to 2 Point 0.2 millimeters fail all the range of 80 kilometers, sorry, 80 kilograms already. Zero point 0.3 millimeters sample failed quite a bit earlier, not to speak of the zero point 0.4 millimeter hook. If we took if we take a look at the weight normalized value, the picture says pretty much similar, only the thicker last became a little better due to their reduced weight. The fracture surfaces are also very interesting because for the thicker layer, the gaps between the filament lines are clearly visible, and the family you go, the more it looks like an injection molded parts. So the first result, you shouldn't go much above zero point 0.2 mm. Sorry for that. So the first result, you should you shouldn't go much above zero point 0.2 mm layer, because that will reduce the strength of your part. And similarly, if we reprint against all tolerances, but in Z standing Z or vertical orientation, we see all of these value taking the loads and break almost at a half strength against XY orientation. Therefore, the ratio calculation between the nozzle diameter and layer thickness enables us to generalize the results. Applying this to our test results mean that starting at layer thickness more than half of the nozzle diameter, we can expect that the strength of the parts will suffer, which means that for strong 3D print and zero point 0.4 mm nozzle, which is normally come with the 3D printers, probably don't go above zero point 0.2 mm layers. Interestingly, I would have thought that really thin layers would perform worse. Hence, the layers don't stick better to each other when they are thinner. Beside the layer height, there are many other parameters that will play an important role in the strength of your 3D prints, which includes printing speeds, extrusion of material itself, part cooling, and especially layer adhesion. And obviously, with this hook, the result we get at good quality on XY orientation, having a good load on that, bearing easily, but setting up with the Z orientation, our parts break maximally at 3 kilogram of load. So again, important is the part orientation must be planned before 3D print. So you have to set your orientation against the load. Otherwise, your part will be break at low loads. Therefore, as per above analysis, we have figured out some recommendations and determine that you should analyze early in the selection process if the part functionality or visual appearances is your first priority. Also, when more than one process can produce parts in the same material, the selection process become a cost versus properties comparison. For functional polymer parts, prefer thermoplastics like SLS or FDM over thermosets, and for the visual appearances and aesthetic thermosets like SLA, DLP or material jetting are the best options. For metal parts, keep remember choose DMLS or SLM for higher performance applications and binder jetting for lower cost and larger part size. Also, for functional parts in metal or plastics material, you can also consider CNC machining. I was thinking that it will take too much time for me to complete the webinar, but we have 15 minutes, so I will try to answer your question. Uh, Rafiullah Katpar says it will be good to see recorded webinar anytime later. Yes, you can contact to our team as I mentioned my email address in the beginning. Let me go back to the first slide where I mentioned my email address. So you can email to us and on this email, and we will send you the recorded link of the webinar, and also you can see the webinar recording on our YouTube page. There's a question from Mr. Jamil Ahmed Dito. He is asking that if we are printing a building or house by using 3D printer, then how can we insert a steel structure at the same time while processing? Uh, Mr. Jamil, I would like to answer your question that now 3D printing is also in civil engineering application, and obviously you people are doing creating their constructing their house from 3D printers. Uh, but about the steel structure, to be very honest, I'm not known about that, but I will suggest you if you can send us your questionnaire on the email, so we will in detail reply you on that. Regarding the CVD points, Mr. Muin will answer you. YouTube page, it's the name with the quality solutions, so you can search on YouTube quality solutions, and you can also see the live webinar is going on in the name of the quality solutions on 3D printing. So you can search on YouTube at live and search for the quality solutions. You can see the live webinar. The question from Mr. Jamil Ahmed: how much 3D printing is efficient than traditional industrial manufacturing process? Actually, the purpose of 3D printing is to check, is to create your functional parts that will be fit within the assembly. So rather to create a mold and doing some injection molding, people can create directly a part from the 3D printer and will apply it into the assembly. Once it is verified, then they can continue uh, the process of their production, like CNC operations, creating the mold, and then produce the injection molding processes as well. But now, if you don't have requirements of the part inconsistently, you can directly print your part from the 3D printer, but keep remember the functional part are all the time produced by the industrial level 3D printer, but also it depends on your application. There are no more questions. I hope that all of your questions are answered, but if we have missed your questions, you can please email me on the on this address. I hope you have enjoyed the session and this webinar is knowledgeable for you, and hope you will join us in our next webinar. Now we are done for now, and hope that there is no more question from you guys. Stay safe. See you in our next webinar. Thank you so much. Assalamu alaikum.